Okay, so let's do some examples of non-homogeneous equations. So like say, here's y prime plus 2y equals x cubed e to the minus 2x. Okay, so when approached with a, what is this thing? Good. When approached with a differential equation, the first thing you should do is try to classify that particular beast. So at the first glance, that's a differential equation. Good, I know which book to go look in. Okay.
First order.
And it's first order. Why is it first order?
Y prime, because it's only prime.
Because there's only a y prime. So I have a first order. It's linear.
Yeah.
Because it's a polynomial in derivatives of y.
Yeah. And it's non-homogeneous.
And it's
Non-homogeneous.
non-homogeneous. Yeah, my homogeneous is going to keep getting shorter, shorter and shorter until it's just an h. Cool? What's the part that makes it non-homogeneous?
It's not equal to 0.
Yeah, there's not equal to 0. But what if I like subtracted that stuff to the other side?
No, it's not a coefficient of the other. So it's still.
Yeah, it's not one of the coefficients of y, right? There's like some extra function of x kicking around that's not attached to a y by multiplication. You guys see that? Okay. How do I start solving a first order linear non-homogeneous differential equation?
Solve homogeneous.
Yeah, solve the homogeneous version first. So, take that thing, drop the non-homogeneous part. Yeah.
So this is called variation of parameters, right?
So right now, I'm just doing some trick.
So are we ever going to learn in this class where this idea came from? Because this is just like a straight up shortcut. Do we like
Do we know why?
Yes.
No.
Okay.
So the reason that this came up, it's like, I'll give you a little bit of it as it goes. First things first, solve the homogeneous version, and the reason that you might try to do this, right? Like motivation for where this came from historically. It's like, I don't know how to solve this, but I know how to solve similar looking things, so I'll start with that and maybe it'll help. Right?
Yeah.
Like you just try something. So what's the solution to this guy?
It's a some constant
e to the minus 2x.
Y of x is some constant e to the minus 2x, maybe?
Sounds exactly that.
Exactly that? Okay. Should I differentiate to check, or are you guys sure? You guys are sure?
Just go roll with it.
Okay. All right, so I got that. Now, you get to pick something. So I'm picking a particular homogeneous solution. The one that I want is the one with the easiest possible choice of constant. What is the easiest possible choice of constant?
1.
What?
4, 0. I mean,
I was gonna
0.
say, then it's the
What is the easiest non-trivial choice of constant? Okay, and then I probably should be totally clear with my notation. This equation is not actually the same as that equation, right?
no.
And so the y's here mean something different than those y's. You guys see that? So I probably should go through and decorate my y's here with h's. And then this is not all the yh's, this is just one of them.
Wait,
You guys see that?
so is that the same YH that equals, oh, okay, yeah.
So yeah, if I was being totally clear with notation, I would say something like this YH with a special hat on it. But I'm not going to keep decorating this friggin' thing, right? I'm just going to leave it at, I'm going to call this YH, and I want you to notice that I made a specific choice of constant there. Right? The reason I don't care about the general solution is that I'm going to absorb that constant into the variation of parameters thing I'm doing anyway. So I don't need it in general, I just need some particular solution that worked. Okay, so I picked a constant. Cool? And the reason I got to pick a constant was I knew I was going to do something else that will pick it up later. Cool? All right, and this is maybe going to Mark's question of like, how would you specifically come across this technique ever? Right? Okay, so the first thing you would do is you would take your solution to your homogeneous differential equation and do what with it?
Maybe plug it back into the thing.
Yeah, plug it back into the first one and see how close you got. What are you going to get?
Wrong.
Wrong. How do you know you? Yeah, because you're going to get 0 on the left-hand side. Why are you going to get 0 on the left-hand side? Because that's the equation you solved. Right? Like, this is not rocket science. You solved the wrong equation. Right? So the solution's wrong. It doesn't work. So what might you guess? Like, what's the next thing you do? Okay, it's, I don't know, slap a constant on it. If you slap a constant on this and plug it back in, what are you going to get? 0. Crap. Like, it's not working. Kick textbook into corner of library, walk outside for a half hour. Right? Like, seriously. And this is really how, like, historically this went. This went like, I don't know, it's not working. Like, I solved this similar thing and it's still not working. Like, F it. I'll go look at trees for a little bit. Then you come back inside later because you're interested in this. Like, you need to solve this differential equation because otherwise the king will behead you or whatever. Like, there's some reason that you have a drive to solve this thing. So what are you going to try next?
Something else.
Yeah, I don't know, slap something else on there. Well, I slapped a constant on there, it didn't work. What am I going to slap on this time?
Function of x.
Yeah, I don't know, some other function of x. Do I know what that function is? Sure. Yeah, try x cubed. Is it going to work? I don't know. But this is like historically, this is how it would go. You'd be like, okay, I don't know, it looks like I got this part, right? Like that's down. Maybe I'll try this thing and see if it works. It might or might not, I don't know. You try it. If it doesn't work, you try something else that seems like it'll work.
So some of these were just like, oh crap, I made it work somehow.
Yeah.
Okay.
Yeah, like the first 10 or 12 times this happened, you were just like, oh yeah, that totally worked. And then somebody was like, guys, seriously? What are you doing? Why do you keep trying particular examples of other functions? Like, just try a general other function and then solve for it. Right, so that's what I'm going to do. I'm going to let y of x be some function that I don't know, u of x.
YH of x, or?
No, so this is going to be the general y that I'm going to try. Right, so this is my guess. And that's really all it is. It's a guess. You're going to guess y should be u of x times what? Yeah, specifically YH. But in this problem, I have a specific YH. It's e to the minus 2x. You guys see that? This is the thing about variation of parameters. Like, where'd my blue marker go? Variation of parameters the whole idea there is that, dude, that's a good guess. Like, that's all it is. That's all most of the techniques in differential equations are. They're just look at the differential equation, classify it as something, remember what the good guess for stuff that looks like that is, then try it.
So if we call it a guess, does it mean that this might fail sometime?
Sure. Yeah. It happens that given this kind of differential equation and sufficient assumptions, like nice assumptions about my functions, and given this particular form of guess, this doesn't fail. But that's only like sufficiently nice assumptions about equations of this form. But yeah, like I want you to have in your head, like this technique might not work all the time. Because if I don't make those explicit assumptions, it might not work. Like sometimes it just doesn't work. Like you just won't be able to resolve the functions, or you won't be able to do the integration or something. You guys see that? Like you can always write down an indefinite integral to kind of get there.
Like we might wind up with an integral of an e to the negative 2x squared or something.
Yeah, sure. Like you might find some integral that you can't do. Right? Is that a great solution? No. Is it some solution? I don't know. Maybe it depends on what you're doing.
What happens if you just guess u of x and absorb the e to the minus 2x into your u of x? What ends up coming out?
You will just translate this differential equation that's in y's into u's, and you still won't have any ideas. The nice thing about this particular guess is that something convenient happens, right? So let's try it and see where that convenience is, because there is some magic here, and it has to do with this is a good guess because. Okay. So what's your y prime here?
U prime of x times e to the negative 2x
Okay.
plus
Minus or minus negative.
Minus 2 e to the minus 2x, right?
times u.
Times u. And I'm dropping the of x's because I don't want to be too confusing with this. Okay, now what do I do with that?
Plug those back into the original.
Yeah, take these two guys, plug them back in your original equation. So plug back into my original equation, I'm going to have a u prime e to the minus 2x minus 2 e to the minus 2x u. Right, that's all. What was all this stuff?
Y prime.
That's all y prime specifically, right? And then there's plus 2, and what was y?
U of x e to the negative 2x.
That was a u e to the negative 2x. And then this is supposed to equal
X cubed e to the negative 2x.
x cubed e to the negative 2x. Why do I not have a question e equals on this one?
Because we're not testing it.
Well, you want it to happen.
Yeah, I want this to be true, right? I'm forcing this, and the reason I'm forcing it is that this is not an evaluate step. This is a solve. What am I solving for? Yeah, I'm solving for the equation u, right? I'm solving for the function u that's going to make my guess the right guess. And I'm hopeful, yeah, right? So, what is the what's the magic of variation of parameters?
Your middle stuff cancels.
Yeah, this stuff, all that is, all that's 0. Why is all that 0?
And so u prime just equals x cubed.
Yeah, that's the magic, man. So the magic is, this part is just a homogeneous equation all over again, right? It happens to obviously cancel here. But the reason it's canceling is that that's the homogeneous equation all over again. Like it's appearing there because of the design of our guess. So this piece is 0, and you have u prime e to the minus 2x plus 0 equals x cubed e to the minus 2x.
The Bible says a to the negative x and integrate.
Yep.
Assuming
So
that
multiplied through by 1 over e to the negative 2x, assuming that,
e to the negative 2x not 0, but that would be
yeah, e to the negative 2x isn't 0, right? It is not, in fact, 0. And you guys can play a little fast and loose with that stuff in differential equations land. Okay, sometimes we're going to have to divide by stuff that might be 0 sometimes.
Could we break that in complex numbers? In e to the stuff? Can we make that 0? Like with imaginary numbers?
No.
I saw some weird stuff.
Yeah, there's some weird stuff there, but no.
What if you, okay, so what if you actually do divide by something that is easily zero? Do you have to factor in the zero?
You might want to worry about that. So what's that gonna affect?
The solution?
It's gonna affect not the solution, but the intervals on which the solution works.
So you would just exclude those?
Yeah, and it should be noted, right, that just because you divided by something doesn't mean there wasn't another way to solve that without dividing by it. You guys see that? So you want to be a little, like, you want to be worried about those things, but they don't necessarily punch holes in your intervals. They might.
Yeah, and it depends on like what you're trying to do too, right?
Yeah. So what I would advise for those is that you look at the existence and uniqueness theorems, but I haven't given you any of those yet. So right now you may as well just assume they punch holes in your intervals, and that's okay for now. That said, they might not. Like the worst case is that they would punch holes in their intervals. So here, what do I get? I got u prime is x cubed. And so, u is a quarter x to the fourth plus your constant. This is a stage where you don't want to forget the constant. Cool. Now, where is your solution to your differential equation? Good, yeah. So the u is just the u, right? It's just the thing that helps your guess out. So you need to take that, or, sorry, it helps your homogeneous solution work, right? So you need to take that thing and slap it onto your homogeneous solution. So you're going to get y of x is 1/4 x to the fourth plus c times e to the minus 2x.
Do you not carry the constant from e to the minus 2x here?
You don't need to.
You already have an constant.
So you have an arbitrary constant right here, and that's enough to fix it up. If you multiply this out, right? So if you kind of distribute, right, you'll see that you'll get, that arbitrary constant, right, plus some function of x times your homogeneous solution.
Gotcha.
Cool. Questions, things? No? Yeah.
I was a little curious as to where that times u came from when you went from y of x to y prime.
This guy?
No, the one that at the very end. No, like at the end of the one you were just looking at. Yeah, I guess you were right. I thought you were
This
looking
guy?
at the first one. Yeah.
So this is the product rule, right?
Oh.
So I had two functions of x that I was differentiating. So I did the derivative of the first one times the second,
Okay.
plus the derivative of the second one times the first. You guys cool with that? And this is one of those things that makes this work. And the magic of variation of parameters is this part right here, where the homogeneous stuff drops off. And once the homogeneous stuff is dropped off, you have, right, a first order linear differential equation in u's now, except that first order linear differential equation in u's doesn't actually have any u's in it. It only has u primes. Right, so this is another spot where you have a little bit of magic, right? And that's what makes that variation of parameters a technique worth learning. Is that if you do this good guess, you get a couple cool things. And that reduces the difficulty of your differential equation in general. You guys see that? What's the solution for this? Or what's the interval for this solution? How do you know it's all real numbers? What are you looking for? Yeah, I was looking for any spot that in solving I divided by 0, or if I look up here, I look for a spot where this first function's 0. Well, that first function's 1, right? So it's not 0, ever. I'm looking for spots where this thing or this thing is discontinuous. Do I have any of that? No. I don't even have spots where those aren't even differentiable, right? You see that? Like, I got better than continuous. I got continuous with all their derivatives being continuous. Cool. Question still? Okay.
Yeah, so do we have to plug this y of x back into the original equation, or no?
That was
Oh,
You totally could. To confirm that you got the technique right, like if you're going to launch a rocket with this, you might want to expend the effort to, like go plug it back in and check.
So you're
Right.
not requiring it though?
No, I don't care.
Okay, cool.
So yeah, for you guys on tests or homework, no, you don't have to plug this back in. What I want you to know is that you could plug it back in. And I want you to know that if it mattered, you should. But like worst case, you get it wrong on your homework. Like, this is not the biggest deal.